Yay! Okay, cool. Welcome back. So we've basically got three more connective rules left. Right? So we talked about disjunction introduction. And disjunction introduction works, and it's so easy because disjunctions are cheap. They're very easy to make true. The problem is, because disjunctions are so easy to make true, it turns out that eliminating them, that is, figuring out what you can derive from them, is actually quite difficult. So we can clarify this a little bit. Suppose we know that A or B is true. Right? Well, when we think about that, there's three ways that could be. It could be because A is true and B is false. It could be because B is true and A is false. Or it could be that both of them are true. And merely knowing that the disjunction is true leaves you in the dark about which of these three options is the case. And that's a problem. Because a lot of times, what you'll be able to derive depends on which one of the two is the case. And if you don't know, well, then it's really hard to figure out what to do. But here's a neat little idea. Suppose that if you could show that, hey, if A were true, you can get to C, and that if B is true, you can also get to C. That is, no matter which place you start from, you always end up in the same location. Well, if you could show that, then you know that no matter why A disjunction C is true, C is going to follow. Again, the intuitive idea. And if it turns out that no matter which of the two routes you take, you end up going here, then we know that no matter why the disjunction's the true, you're going to get this result. This is the idea of disjunction elimination. It says, okay, you've got a disjunction on your proof line. Well, if you can show in one subproof that the left disjunct gets you to C, and then in a second subproof that the right disjunct also gets you to C, the exact same sentence, then you know no matter which way you go, you're going to end up at C. So you can kind of think about it metaphorically like this, right? You're on one side of a mountain. You want to go to the coastal town on the other side. You can go the east road, you can go the west road. No matter which way you go, you end up at the coastal town. So it don't matter which route you take. You're going to end up there. That's the idea behind disjunction elimination. You take your disjunction, you have your two subproofs, one that shows you going one way to the destination, and the other that shows you the other way to the same destination. And then you know that the destination, that C, follows. Now, notably, this is the most complex rule. In order to use this rule, what you have to have, you need to cite the disjunction that you're eliminating, and you need to cite the two subproofs. So again, that's the kind of general idea with disjunction elimination. And it derives from the fact that disjunctions are so cheap. They're so easy to make true. What we do is we say, okay, then we'll give you something that follows no matter how they're true. So this is disjunction elimination. Right? So now we've got conjunction intro and elimination. We've done conditional intro and elimination. We've done the biconditional intro and elimination and disjunction. All that's left is negation. Now, unfortunately, negation is weird. And the reason it's weird comes back to something we were talking about a few minutes ago. When we're playing with natural deduction, we don't think about whether sentences are true or false. If they're on the proof line, they're true. So in order to talk about a sentence being false, the closest we can do is say their negation is true. To play around with negation, I'm going to have to introduce you to a very weird symbol. You might have come across it before. Have people ever seen this before? This little upside down T? So this is a symbol to represent contradiction. Basically, this is going to be both really bad and really useful. So let me talk you through it. Here's negation introduction. Negation introduction, the idea behind it is if something being true leads to a contradiction, then it must be false. So if you have a subproof that starts with a sentence and the subproof ends with the upside down T with a contradiction, then you know the thing you started with must be false. Note that this one actually is another Beyonce rule. This one gives you something to the left. But importantly, it's not a conditional. It's a negated sentence. Because the idea here is, hey, if this were true, bad things, so it must not be true. So negation introduction is interesting because it's one of the very few non-conditional ones that goes to the left. So that's negation introduction, right? Again, we have a subproof, starts with a sentence, ends with a contradiction, you derive it's negated. What about negation elimination? Well, negation elimination is also known as contradiction introduction. It says if you have a sentence and its negation on the same proof line, right? Note it has to be on the same line, then you can derive on that line a contradiction. So if you have a sentence and its negation, we don't care how you get it, but if you have those two, then on that very line that you're on, you can introduce an upside down T, a contradiction. And again, you can call this negation elimination because you're using the negation. You can also call this contradiction introduction. In fact, I think Tim mentions both of these names, right? I'm going to call it negation elimination. So one thing that's interesting, here's something very cool. This rule is the only way to ever get one of these. That's why this is contradiction introduction. So going back a slide, you know a rule that has to happen in this subproof. A rule that has to occur in this subproof needs to be negation elimination, because that's the only way you could have derived this contradiction. Something we'll talk more about as we go along. Yes, sorry.
But how do we do that if you need a negation introduction to have?
Good. So what this means is that a lot of times we will have to already have a negation somewhere along the lines. It will be one of the sentences we started with as an assumption. Or we'll be able to generate a contradiction with some other negated sentence and itself.
Do we ever get like a contradiction in the main line?
Ah, cool. So note, this can be the case regardless of what line we're on. It could be in a subproof, it could be on the main line. This is why I said these are bad and good. So here's my favorite rule. My favorite rule is the next one. Right? Again, negation elimination, we generate the contradiction. Let's use it. Let's blow it the fuck up. Explosion is the best rule. It's also called ex falso quod libet, or anything follows from a contradiction. The rule is, if you have the upside down t, on that same line, you can derive absolutely anything you want. Anything. Any sentence of any structure doesn't matter. If you have a contradiction, you can get anything. If you have the upside down t, you can blow it up. Now, why? Why might we buy this rule? Let's go all the way back to lecture 1. Remember Mars's moons? And we talked about the weird case when premises are jointly inconsistent. And when premises are jointly inconsistent, doesn't matter what the conclusion is, the argument's always valid. That was this rule. The basic idea is, if you're silly enough to believe a contradiction, you're silly enough to believe anything. I often pitch that in a slightly harsher term than silly, but we'll just leave it for that. Right? So that's the thought here, right? Because this could never be true. And since this could never be true, well then whatever you want is going to follow from it. Explosion is very useful. Explosion is very useful. So this could be something that, hey, we derive a contradiction in the main line, let's blow it up and get anything we want. So that's one option. Okay.
Nihilism.
It's not nihilism, it's everythingism. Because this can be everything you want. Right? So this could even be a sentence that we know is false, right? A conjunction, not A. It can be any sentence you like. It's trivialism, actually, is what it's often called. Right? So, okay, right? These trio, negation, introduction, negation, elimination, and explosion, they're all a tightly bound set. Usually, when you find this one in the subproof, you will have used possibly, maybe, not possibly, maybe, definitely this one, and sometimes this one as well. They all go together. They all hinge around producing or employing or making use of the contradiction symbol. Okay, cool. So there's just a few more main rules left. One of the last ones is TND, tertium non datur, or if we're not being very posh, no third way. And the idea of no third way, well, actually it's basically a kind of disjunction elimination, but it's using an implicit disjunction. So here's the thought. If you take a sentence and you can show that, hey, if this sentence is true, we can get to B, and you can also take its negation and show that, hey, if its negation's true, we can get to B, then we know that B must be the case. Because A must either be true or it must be false. And no matter which way you go, you end up at the same result. So it's a version of disjunction elimination. Just in this case, hinging on the disjunction of A or not A. So for this rule, 2 subproofs. One that starts with a sentence and ends in a sentence, in sentence B. And a second one that starts with not A and ends in the exact same one. It ends in B. Okay. So again, TND is kind of a version of disjunction elimination, but it strictly doesn't need the disjunction to be there. Whereas disjunction elimination, you always have to have the disjunct. These are all the rules. That's it. You've got introduction elimination rules for each of the operators. You've got the explosion rule, and you've got TND. You can now, with these, construct any natural deduction proof. Or to put it another way, using these rules, you can specify how an idealized reasoner would make some inferences to go from a premise to a conclusion. You can show how to get from assumptions, from premises, to a conclusion. So instead of merely assessing whether an argument's valid or invalid, you can show how it's valid, how to go from the premises to the conclusion. And that's what we're going to be doing. So we're going to work on a bunch of different things. Now note, much like when we had some of the other features, things like joint consistency or joint tautological equivalence, these kinds of things. Sorry, tautological equivalence. We had all of these semantic properties. We're going to have similar proof theoretic properties. Validity isn't the only thing we can do with this system. We'll talk more about that stuff next week. But this is it, basically. This is the sort of stuff that will let you build all the proofs. Now, before we turn to the last little part here, again, I want to pause, ask, what questions do you have for me so far? I absolutely understand this was an assault of information. There's a whole bunch of rules here. One of the easiest things, the best way we'll get to get grips with this is practice. Because, well, we got a lot more weeks left, and this is all we're going to do. So you can bet we are going to do a hell of a lot of natural deduction proofs and tutorials. It's going to be awesome. Genuinely so much fun. Now, before we wrap up, okay, if we're up for it, I want to finish by talking to you about some derived rules. These are ones that, strictly speaking, aren't in the system, but we have there to make our life easier. We don't have to have them, but once you know them, your life's simpler. So we'll talk through them real quick, and then we'll wrap up. So these derived rules, again, aren't strictly speaking part of the package. They are generated. They depend on the other rules, but they're shortcuts. They make our life easier. Here's the first one, the easiest one, reiteration. If you have a sentence, you can repeat it. That seems really silly, but there are times when it's very useful. Yes? Yes, it will. Right. So again, we'll just go back. Again, this is, if you have a sentence already, you can do reiteration to repeat the same sentence. So let's look at this argument. This argument, valid, invalid. It's valid, right? It's valid because it says A or B, not B, so it must be A. Remember way back in like lecture 2, we talked about this one, I think? I can't remember if it was 1 or 2. Right? So let's prove it. Let's construct a natural deduction proof. So the first thing we do, we start by writing all of our assumptions down. We draw our proof line going vertical and our assumption line going horizontal. Now we want to get to A. We know that this is where we want to end up. So what do we think we're going to do? How could we get to A? Well, we basically only have these two sentences to work with, right?
Conjunction, elimination.
So it's not conjunction. What operator is this? Disjunction. It's disjunction. Disjunction elimination. We're going to do disjunction elimination. Yeah? Nice. How does disjunction elimination work? Do we remember? So it's the one where you have to go both ways and get to the same place. So we're going to need two subproofs. One that starts with A and ends in A, and one that starts with B and ends in A. We need to show that no matter whether you go through A or B, you end up in the same place. So let's do that. Suppose we start with B. Well, how can we get to A? We can generate a contradiction. Right? Because at line 4, right, where we are, we've got 1, 2, and 3 available to us. So what rule can we use at line 4? Nice. Do we remember what else it's called? It's negation.
Elimination.
Bingo. Negation elimination gives us the upside down T. Okay, cool. Well, we've got a contradiction. That's not what we want, because we want this subproof to end in A. So how do we go from our contradiction to A? It's my favorite rule. Yeah, what rule is it? Do we remember? Boom. Blow it up. We get A. We can get any sentence we want. But in this case, we want to get A. And we know we want to get A because remember, the whole idea was to use disjunction elimination. We want both subproofs to end up at A. So nice. We've got one of our two subproofs done. We are Bon Jovi'd. We're halfway there. Now all we got to do is do the other subproof. So what does it start with? What's the second subproof start with? It starts with A. Right? It starts with A. Because we've shown from this disjunct, we can get to A. Now we show from this disjunct, we get to A. So in line 7, we need to somehow derive the sentence A. We can get sentence A. What rule can we use? Reiteration. Right? Reiteration. Hey, guess what follows from A? A. Thanks. But note, that was helpful. Because what do the two subproofs now show? No matter where you go, you get to A. So what can we put at line 8? What sentence can we derive at line 8? We derive A. And what's the rule that we used? Oh, so now it's harder. Disjunction elimination, right? We used the disjunction in sentence 1. We went through our two subproofs, showed that they both result in the same place. So sentence A follows from the disjunction sentence in 1. So again, what did we do here? Let's talk about the whole process. We started with these two premises. We thought about, okay, we want to get to here. And the way to do it was to go through the disjunction. Show that sentence A followed from both options here. So nice. Valid argument. We've now shown why. Here's something really cool. This also gives you a derived rule. The derived rule is disjunctive syllogism. Here it is. If you have A or B, and you have not B or not A, then you know that the other option's true. So instead of going through that 8-line proof that we just did, you can do it in a line. Disjunctive syllogism says, hey, you have A or B, and you have the negation of one of the disjuncts, it doesn't matter which one, then you can derive the other remaining disjunct. Yeah?
We get the derived rules in the exam as well.
I give you all of them. No problem. So again, this derived rule, it basically says, hey, you know what I could do? In the background, there's this argument that doesn't use DS, but I'm saving us all some time and space by just saying, hey, trust me, I could do it, but I'm just cutting out some lines. This is what all derived rules do. Yes?
This is kind of a bit unrelated, but the tautologically entailed symbol, which is like straight and these two lines, is it based on this?
Close. Next week, we're going to introduce the single turn style. So remember that was the double. This has to do with semantics. The single turn style has to do with syntax alone. We'll talk more about it next week. But yes, we'll come back to that. So, okay. Again, we've got disjunctive syllogism. This is a derived rule, just like, gotta go back. Just like reiteration. There's two. A third derived rule is modus tollens. So modus ponens was where we had the conditional and the antecedent, and we derived the consequent, right? We had the conditional and the first part, so we concluded the second part is true. Modus tollens says you've got a conditional, and you know the second part is false. The consequent is false. So then you can derive that the first part is also false. The antecedent must be false as well. And the reasoning here is good, right? If you know the conditional is true, it's on your proof line, and you know that the consequent is false, well, the only way that could be consistent is if the antecedent is false as well. Because if the antecedent were true, the conditional would have to be false. So modus tollens basically, again, compresses this proof down, saves ourselves some lines. Okay. Another derived rule to make your life easier is double negation elimination. If you have not, then you can derive a sentence minus those two negations. Note, we have double negation elimination. We do not, unfortunately, have a rule for double negation introduction. We'll talk more about how you can introduce a double negation in the tutorials this week. So if you have not, you can derive a sentence without both negations. Note, though, it needs to be the main operator, right? The two negations need to be the main operator. So if there's a conjunction in the way, you have to go through the conjunction to get down to just those. And the last quartet of derived rules are going to look slightly terrifying initially, but they're actually very simple. And they're equivalences that we've used a bunch. They're called the De Morgan rules. So first one is, if you have a negated conjunction, then you can derive the disjunction of their negations. Right? And the same thing the other way. If you have a disjunction of two negations, then you have a negated conjunction. Okay? This one maybe isn't as terribly familiar as the next pair, because the next pair, well, what are they going to be? It's how we do neither nor. If you have a negated disjunction, that's equivalent to a conjunction of two negations. Similarly, if you have a conjunction of two negations, then you can derive the negated disjunction. These are, again, simplifying. They help your life out. They're not going to come up that often, but they're useful to have in your back pocket. This is it. This is literally every single rule that there is for natural deduction for TFL. The things to remember, and I'll point this out before we move on. Things to remember. Almost all of these rules, you have to stay on the same proof line you're on. There are very few that let you take things from a subproof to the left. The thing to remember is what those rules are and what they let you do. Okay. Drill that into your head. Knowing that, we will be able to progress on. So, what we're going to do next week is more of this. So in particular, we'll talk again about how these rules work. And then what we'll do is actually generate a bunch of, we're going to call them syntactic properties, which are going to be parallel to a bunch of the semantic properties we defined, but they'll all be understood in terms of our natural deduction machinery. So importantly, for this week, don't worry, go ahead. Right. What we're going to keep working on, though, is figuring out how to construct these proofs. Right? This is what we're going to keep working on in the tutorials. So don't freak out if it's just not clicking yet, right? We're going to work on this a lot. Have an attempt at some of the questions before the tutorials this week, but we'll go through these, try and get clear on all the rules and everything. Thanks for coming, guys. Take care of yourselves, and I'll see you all later this week.